Hey folks, we're at the end of the energy unit, and this next topic is going to be fairly separate from everything else. In fact, I would say that it is questionable whether this is a great use of your time during the end of the semester crush. So watch this video at some point in time. It gives a little bit of a different perspective on potential energy. Hopefully you find it interesting. It is very rare that a question pops up on the AP exam on this topic, but it, again, is going to attempt to give you a more complete picture of potential energy. So we have this equation for gravitational potential energy. And so this is only valid on Earth because this is, first of all, relative to some location where there's zero gravitational potential energy. And that location can change depending on what you're doing as a physics student. And it only works for a uniform gravitational field. And so as soon as you start to climb to higher and higher altitudes, the value of little g changes, and uh, therefore the amount of potential energy depends not only on the mass of the object and its distance, but also the value of the gravitational field. So, when we studied gravity, we learned that little g is equal to big G times m over r squared. And so you could like put that in, but it kind of gets out of hand as soon as you get far enough away from one planet and you're like close to another planet. So a more complete way to do this, and the reason it's called universal gravitational potential energy is that it's based on Newton's universal law of gravitation. And it does something kind of quirky. So gravitational potential energy out in space is equal to negative big G times the product of the two masses involved divided by the distance separating them. So this is gravitational potential energy anywhere in space for any two objects. This equation, again, assumes that one of the objects is the Earth. This works for any masses, any two masses anywhere in the universe. And so the idea is every pair of masses in the universe stores energy as long as they are some distance apart. The reason for the negative is a little bit more complicated, but let's just kind of look at a graph of this function, and then we can start to maybe understand what's happening. So I'm going to draw the fourth quadrant of a graph. And so it's going to be a graph of gravitational potential energy versus distance. And the origin is up here in the top left-hand corner. The reason we need this quadrant is because all the values of r go from 0 to infinity, and then the maximum value of ug is actually going to be 0. And so all the values of ug are negative. If r is very, very small number, then this fraction will have a very, very large value. And because it's negative, it will have a very, very large negative value. So the graph kind of starts like this. And then as r gets closer, we see that there's an inverse relationship between r and gravitational potential energy. So the graph starts to do this. There is an asymptote on the y-axis and an asymptote on the x-axis. In other words, we view it as impossible that the two objects could be a distance of 0 meters apart, because then they would be the same object. And we also understand that no matter how big we make the value r, this value isn't 0. It can approach 0, but it's never 0. And so we have some new way of thinking about things. We think about gravitational potential energy as something where the maximum possible value of it is 0. In other words, if we take r and bring it to infinity, which we can't actually do, but if we were to bring two planets an infinite distance apart, they would store 0 energy between them. The closer they are, the more energy they store. And so the reason why it's negative is because in physics, we often think about, we haven't done it yet, but it is often thought about that the amount of energy stored between two objects is the amount of work necessary to bring them to that configuration. So in some situations, we would start with them like together and move them apart. In this situation, we start with them an infinite distance apart and bring them closer together. And then they store some sort of energy with one another. So if we're talking about like a person on Earth, right, 0 meters away would be if you travel to the center of the Earth, and then as r increased, you'd be traveling like outward through the innards of the Earth. And then at a certain point in time, you would reach a value of r that is equal to the radius of the Earth. And so if I drew a line like that, so that, I didn't draw a straight line, but I tried, that distance would be the surface of the Earth, right? So again, to be at 0 would mean you're in the center of the Earth. And then as r increases, you'd be moving outward toward the surface of the Earth. Once you got to the surface of the Earth, you would be at a distance equal to its radius. And so that is associated with some amount of gravitational potential energy. So specifically, that would be equal to if you had the mass of the, if you had the Earth, if one of the objects was the Earth, there is some amount of gravitational potential energy that's associated with the radius of the Earth. This is also therefore equal to, for us, 0 potential energy. So in all of the energy work that we've done so far, this value, if we use this equation, this is where we have a 0 value. And so our like little energy equation starts here and goes up from there. So in our world, all of the energies are positive or 0, because here's the lowest point, and then this is a higher and higher altitude as we go. And for us, it's a straight line. This is more in line with what we know about physics, which is as the strength of the gravitational field changes, you store energy at a slower and slower rate until you're eventually not storing any more energy by going further away. So it just kind of like resets the field, whereas if you use this equation, it has to be like on a planet and at small altitudes. This can now be used for any two objects anywhere that are some distance apart. And so the idea being like, let's say you had, and this is the, the only type of problem that tends to show up on the AP Physics 1 exam is something like this. Let's say you have 3 objects floating in space. You can't see that. Let's say you have 3 objects floating in space, and they are all equidistant to one another. So they essentially trace out a triangle. So the lines that I'm drawing are not real lines. They're not really there, but the objects are really there. So 3 objects kind of floating in space. And the question is basically like how much energy is being stored between them. And so we can call them like M1, M2, and M3. The total gravitational potential energy that's being stored between them is, if we tackle each pair individually and add their energies. In other words, there is potential energy being stored between these 2 masses. There's a different amount of energy being stored between these 2 masses, and still a different amount of energy being stored between those 2 masses. Now, I put in just letters. You would then have to use, G, negative G, M, M over R for each term and add it up. Because all 3 of them have the same mass, because they're all the same distance away from one another, the gravitational potential energy that's stored between them is going to be equal to negative 3 G mm over R, because there's 3 pairs of masses that are storing energy, 1, 2, 3. Their potential energies add together. Another way to think of that is if I started to move M3 around, it would change this value of potential energy and this value of potential energy. So that's all for this lesson. Again, like there's no practice problems really for it. I can eventually show you the one practice problem that there is on the AP exam, but it's a rarely tested topic and hopefully one that was a little interesting for you. Thanks.